Now we're on record. So where were we? So we have two applications, and the first one is actually an application of category theories, because I actually think it saves time when you assuming that you know all the infrastructure about groupoids. The second one is not really application, but it's a reinterpretation, a nice way to think about things that you already know. So the first one is in algebraic topology. It's Van Kampen theorem. So does anybody needs me to recall the formulation of Van Kampen theorem?
No.
So everybody know what it is about, yes? I will still recall on some level, but I just want to know. Okay, so we have two open sets, and we know U1 and U2, and their union is X, and we know pi1 of U1, pi1 of U2, and pi1 of the intersection of U1 and U2, and we want to compute pi1 of X. So you probably usually know that usually you ask that the intersection will be connected. Because if it's not connected, it's not really clear how to even formulate the theorem. Yeah, so X is connected is somehow not a real condition, because if it's not connected, just do it for each piece separately. But you can have an actual interesting situation when U1 and U2 are connected, X is connected, but the intersection is not connected. And then you get something interesting, because U1 and U2 both have trivial pi1, and the intersection have kind of trivial pi1, except of its pi0 is not trivial, and the union have non-trivial pi1. So we want to formulate it in case, in the general case. So it's a bit cheating, because we give a formulation in the general case, but it's rather cryptic, and in order to encrypt it, it becomes much easier if it is connected. So, but what we will do, instead of considering little pi1, we'll consider large pi1. So do you remember what is the fundamental groupoid of a topological space? Yeah, so
Passes modulo homotopy.
what? Passes modulo homotopy. But now I do not consider only closed passes, so I consider actual groupoids. So my object will be points in the topological space, so many objects, and morphism between two objects will be the collection of all passes up to homotopy. So, yeah, so if there is holes here, then all those paths different, and otherwise I mostly will be the same. So it looks like have nothing to do maybe with pi1, with little pi1, because it have many objects. But when you think about it, if it is connected, then there is only one isomorphism class of objects. So if X is connected, then capital pi1 of X equal to B little pi1 of X. Yeah, so this is a simple exercise. So once you believe this exercise, you see that there is no too much difference between capital pi1 and little pi1. And you remember we talked about push outs of groupoids, and we say that if it is BG, then it's kind of simple object, but if for general groupoid, it's a bit cryptic. But here is a answer, like the groupoid formulation of Van Kampen theorem, that pi1 of X, theorem, pi1 of X equal to the push out pi1 of U1 over pi1 of the intersection with pi1 of U2. And of course, you can also formulate it for more than two open sets, but it will become a little bit more cumbersome. So you will have to discuss some other limits which are a bit more problematic. And okay, so this one thing that category theory gives us is kind of gives us a nice way to formulate Van Kampen theorem, but also it simplifies its proof. And what do I mean by simplify its proof? So you can look at Hatcher as the original proof, and you see that there are like two levels there. Like you can, if you read the entire chapter in Hatcher, first you do some basic things about pi1, homotopy lifting property, etc. And then everything is kind of one-dimensional. So your basic object is a curve, and a curve is a map from the interval to some set to some topological space. And when you want to prove things about it, for example, homotopy lifting for coverings, we will discuss it partially in a minute. You usually use the compactness of the curve, and the compactness of the curve of the interval says that you can, if whenever you have an open cover of the interval, you can present your interval like as a union, disjoint but touching union of many closed interval, or not disjoint, yes. So let's break it down into shorter interval, and each of the short interval is lie entirely in some open set, so it's small enough for some perspective. And then you do things by this induction, by this sequence. And most of the chapter in Hatcher uses this trick, and basically this is it. And this way you can prove homotopy lifting properties and other stuff. But then when you come to Van Kampen theorem, you see that the argument is not one-dimensional. It's essentially not one-dimensional because you have to discuss homotopy between passes. Yeah, so Van Kampen theorem have two parts. So if it is not groupoids but just groups, so what you have here, the coproduct becomes just a amalgamation product, and you clearly have a map, I think, to this direction. Of course, any closed path in U1 give you a path in X, and a closed path in U2 give you a path in X. So you have a map to one direction, and you want to prove it's one-to-one. You want to prove it's onto, and the fact that it is onto is rather easy. It's essentially one-dimensional argument. You want to show that any curve in X can be obtained from curves in U1 and U2, and this you do using this trick of breaking down the interval. But the fact that it is one-to-one is indeed more tricky, because you consider you want to prove that any two passes that homotopic here are also homotopic here. So homotopy between two passes is something two-dimensional. It's mapped from a square. So the proof becomes two-dimensional. And of course, it's not a big deal. You have an open cover of a square, and now instead of breaking it to small pieces, you're breaking it to small squares. And then what you usually did in the one-dimensional case, you do here in the two-dimensional case by somehow going by the squares by induction. And it might become even more tricky if you have more than two sets, U1 and U2. So you don't really like 4 squares to meet at one point. You want all 3 squares to meet at one point, and then there's this weird thing of moving a little bit each of this line right or left, and then everything works. So it's not essentially new stuff, but it is harder. It's two-dimensional mathematics is harder than one-dimensional mathematics. And I think category theory basically shows you that you can avoid it, or in fact you can translate the geometric difficulty into algebraic or combinatorial difficulty, because two-dimensional things are passes in the loop space. Are basically one-dimensional thing in something much larger. So yeah, so you can translate the difficulties, but it's hard to do it by hand. So and this is why you want to use category theory. Okay, so we don't translate the entire difficulty into the world of of category theory, there's still some geometry or some topology to do, but all this geometry and topology is one-dimensional, and it is inside homotopy lifting theorem. And the main corollary from the homotopy lifting theorem, and this is what we're going to use, is the following theorem. Under some reasonable assumption of X, that we will always use some locally connected, locally simply connected, whatever. So that so we have coverings of X, and we have functors from pi1 of X to sets. So now we have functor to one direction. Let me see what is that direction. Yeah, I think the most natural direction is this. No, sorry. No, maybe there is no. Yeah, so okay, so it's theorem, but together with an actual construction. So those two categories are equivalent.
There are natural maps in both direction functors, but
one have to construct
neither
them. Yes,
of them is completely obvious.
Yes. Yes. So yeah, I think maybe this one is a bit simpler because this is actually a homotopy property, and it does not use as locally simply connected. It does not use as a construction of the universal cover. This one actually needs a
it gives to every point this fiber, and you just need to say that you can lift paths.
Yes, and which is homotopy lifting. But okay, so the actual construction is what actually important. Maybe I can say what I want from the actual construction, but the homotopy lifting theorem, together with maybe the existence of universal covering, give you equivalence between those two categories. So let me describe this down arrow. Once what the guy said, for each point in X, so you want to construct, you have a covering, you want to construct a functor from by one. So for each point of X, you can consider its fiber. And now if you have 2 points and path between them, you want to consider a map between one path fiber and another fiber. And this is exactly homotopy lifting or path lifting. That you have a path downstairs in the covering, and you know how to lift it in the beginning point, so you choose point in the cover. So there exists a unique lifting of this path upstairs that would be actual lifting, yes. So there exists a unique lifting of the path. And this gives you, for any choice of a point in the first fiber, a choice of a point in the second fiber, so it basically gives you a map between two fibers. And if two passes are homotopy, then it gives you the same point. Homotopic, and it gives you the same point. And this is really indeed, yeah, it is rather simple because the lifting is unique. So if there are two homotopy downstairs, and it will also be homotopic upstairs. It's also kind of two-dimensional argument, but it's essentially one-dimensional. You don't really need any squares here. Yeah, so the statement that this functor is equivalence of categories, it's a bit more complicated because it actually includes the notion of universal covering. So the universal covering is, you start with some specific functor here. Let's say X is connected, and then pi1 is just a little pi1, and then you just take like the action of a group on itself, and so and this will give you the universal covering. So the universal covering is a covering such that the fiber at each point is just pi1. So the functors of the other direction give you the universal covering. So okay, so this is the theorem, and this we use as an input from algebraic topology. I promised that I would say what do I need from, instead of, so I indicated the proof of this theorem, but instead of saying the proof, I want to formulate what do I actually need from this equivalence. So maybe the best thing that I want from this equivalence is the fact that it's functorial. It's commute with restriction. So what do I mean by it? So if we have u inside X, open set, open. So we have a functor from covering of X to covering of U, just restriction. And I have a functor from pi1 of U to pi1 of X, just by restricting, no, not restricting, just by sending each point of U to point of X. So I also have a functor to the other direction restriction from functors from pi1 of X to wherever, in particular sets, to functors from pi1 of U to sets. Okay, so let me write it here. Funct pi1 of X to sets fun from pi1 of U to sets. So when we said that the Incumbent theorem gives us vertical arrows, say like this. So I want this diagram to be commutative. Okay, frankly, I need to be more careful because it's diagram of category, so I need to explain what do I mean by commutative diagram of categories. Okay, but in this case it's not so hard. So you have two compositions like this and like this, and you don't ask them to be the same. You want that you will have an isomorphism. Maybe you need something. Okay, everything now become. I think you just can choose those vertical arrows in such a way that you will actually get an equality. But if yes, you can do it, and anyhow you can write another commutative diagram of what you want from those isomorphisms. So if you have X and inside is a subset U, and inside the subset V, so you can go down from X to U and then to V, or you can go directly from X to V, and then you get two isomorphisms and you want them to be the same. So it's a bit annoying, but basically it's the only thing that you want to expect.
Can you repeat again? I didn't understand how the functor acts and what its relation to Van Kampen theorem.
So not Van Kampen theorem. I said Van Kampen theorem. I mean homotopy lifting theorem. So
Okay.
I reformulate homotopy lifting theorem as an equivalence of two categories. So the problem with this reformulation that it's bad. Yeah, it's bad formulation just to say that two categories are equivalent. It's not enough information. I want that some explicit functor between them will be equivalence. So this equivalent specific functor is the one that's given by homotopy lifting or by passive lifting. So I formulated. I proved basically this theorem, or I explained how to construct a functor to one direction. And this is nice, but
I just don't understand.
Just a moment. Just a moment. So I explained how to construct this map, but this kind of proving the theorem instead of formulating it. And now I wanted to say how without constructing an explicit map, what do I want from this map when I formulate this theorem? What do I want from this map? And the reason I draw this diagram is to explain what do I want from that vertical map. So, Tal, you still want to ask something?
Yes. Did you actually explicitly describe the functor in one direction? Because you
I
said
did
homotopy
before.
lifting.
No,
You say
I
that
did. Yes, I did this. I did describe the functor from the downstairs, but now I don't want to use this description. You want me to repeat the description?
yes, because basically you say the lifting, and I don't understand
Okay,
how
so
it's
let me
related to the
explain.
functor.
Okay, let me explain.
Thank you.
You want to start with the covering and construct a functor like this. Yes? So I want to go downstairs. I start with the covering and I want to construct a functor like this. So how do I construct a functor like this? I have object in pi1 of x. Object in pi1 of x is just a point in x. Now I want to give a set to it. So this is very simple. I have a covering, so I just consider the fiber. But this is not enough in order to define functor. I also need to describe what it do to morphisms. So now I have another point and another fiber, and I have morphism between these 2 points. But morphism in capital pi1, it is just a path between those 2 points. Now I have point here, and path between them, and I want to construct a map from this fiber to this fiber. How do I do it? I start with a point here, and I say let lift this path to a path upstairs that will pass through this point. By homotopy lifting theorem, there exists a unique way to do it. And the end point of this way will be just the point where I map this first point. So homotopy lifting gives me the way the functor acts on morphisms. Of course, this only explains how for any covering I construct a functor. Now I need to explain how to map between 2 coverings, I construct a morphism between 2 functors. But this is already easy. But now I want to ignore all this explanation and say, no, this is part of the proof. What is the formulation? What I actually want from this functor that's going upstairs and downstairs. I want the functor to be equivalence of categories, but not arbitrary one. I want it to behave well with restriction to open sets. And this is why I draw this diagram. So I have covering over x, covering over u of u. I have a restriction functor, and now I have those 2 those 2 categories, each of which is equivalent to the category above it. And here I also have a restriction functor. Downstairs I have also horizontal restriction functor. So I want basically that this upstairs restriction functor will coincide with the downstairs restriction functor after we identify between the categories upstairs and downstairs. And the last comment that I said that I have to be careful because we don't really identify between them because they're just equivalent, they're not isomorphic. And so we have here two functors. We want the diagram to be commutative. So we have 2 functors, but we can't ask them to be equal. We have to ask them to be isomorphic. So frankly, we can ask them to be equal. We can choose everything in a way that they will be equal. But if we want to work properly, we should not ask them to be equal. We should ask them to be isomorphic, but we should not ask them to be abstractly isomorphic. We should be given this isomorphism. It's part of like something that if we want something to exist, we want to give it a name and then ask what conditions it should satisfy. And it's easy to see what condition it should satisfy because if we have u inside x and inside u we have some v, then we see that we can go from x to u restriction and then to v, or we can go directly, and basically we can get 2 diagrams of isomorphism between functors. We can get diagram of isomorphism between functors and ask this diagram to be commutative. So I don't want to write it because it makes it over cumbersome, and I did give an explicit construction of the functor, and in fact you can even ask for equality in this case. But I want you to know that if you want to do everything properly, you basically need to go through many words.
I have a question. If I understand correctly, for every object in the category of topological spaces or nice enough topological spaces, you associate natural transformation such that the diagram commutative diagram of topological spaces of of categories that associates here is commutative. Does it have a name in general categories?
Probably. So probably it's isomorphism between. So we have but here we have to be a little bit careful. We don't want to go work in the entire category of topological spaces. It's too large. We don't want everything to be functorial with respect to it. So we want not only some conditions to satisfy. We also want to consider not all the morphisms, but only open embeddings or some other. Oh yes, maybe some coverings, but not general morphisms. And then yes, you're probably right. So you can do wave top, and wave pi1, which is functor to groupoids. And here we have to be careful because the second is two category and not one category, but whatever. And we have funct from something to set. So this is functor to categories, but you can ignore it and think it's functor to groupoids because you can consider only in the when you do this category functors to sets, you can replace it by the groupoid of functors to sets. So any category you can replace by its groupoids basically when you erase all the morphisms which are not isomorphisms. So this is probably not a direct, not a covariant functor, but contravariant functor. So somewhere I need to write op. Let me write here op. And you have covering, which is also functor to category op. And yes, so we want this diagram to be commutative. This is a property. But it's diagram of two categories of functors between, so it's functor between category, some of those are categories and some of those are two categories. So we have to be a bit careful. Okay, so this for me what I want from homotopy lifting. And now we want to prove Incumbent theorem. What is time? So what do we have? We have pi1 of x. We have pi1 of u1. We have pi1 of u2 and pi1 of the intersection. And we want to prove that this is a push out. Let's say it's not the push out, but we have here the push out. And we remember basically by definition of push out that there exists and unique up to something map like this, such that this diagram is commutative. But this diagram of categories, but yet we know what is a push out. Did I give the correct? Yeah, I think I give the correct direction. So so since we have this diagram already, so we already have this functor. We only want to prove that this functor is an actual equivalence. So now consider this diagram and apply to this diagram the construction of taking functor from a groupoid to all the functors from the groupoid to sets.
Wait a second. You didn't prove that the push out exists.
Of groupoids?
Yes.
I did said it, and I did say that if the groupoids are connected, if they're BG, then it's more simple than it's just an amalgamation product. I said it's some localization, and localization exists in general, and I think in this case it also satisfies our condition. So how bad can it be? No, it's not satisfied. It does not satisfy our condition. Yes, the construction is it's ugly, but it's rather straightforward. It looks like amalgamation product. Yes, it's long words of it's basically what you expect it to be. So now apply to all this diagram functors from a category to sets. and use the homotopy lifting theorem. So each time we have pi1 of something, we will get the category of its coverings. So what will we get? Coverings of U1 intersection U2. So this is contravariant functor or two functor. We have restrictions now from coverings of U1, covering of U2, coverings of X. Okay, and coverings and functors from the push-ups out to sets. So here are some things that have to be proven. That this construction of taking functors to sets commute, or not commute, but maps push-outs to fiber products. Okay, let me leave it as an exercise. Exercise. Functor from push-ups out gamma 1, gamma 2 over gamma 3 to sets is canonically equivalent to the fiber product of functors from gamma 1 to sets times functors gamma 2 to sets to functors from gamma 3. I don't have place to write it. There is no gamma 3, sorry. No, gamma 3 is here. Here is gamma 2, yes. And here again, I have to be a little bit more careful because functors from something to sets is not a groupoid, and I did not define fiber product of general categories. But first of all, you can define fiber products of general categories, and alternatively, you can just say, let's ignore the actual category and consider only the corresponding groupoids. So what I claim is here I have the fiber product. Let me just call it F. And I have a functor to this direction. So now good news. What is covering of X? Yes, it's a map between some topological space to X that satisfies something. So if we have covering of X, of course we can construct a covering of U1 and covering of U2. And of course, if we restrict it to U1 intersection U2, we just get the same covering because it's just a restriction of this one directly here. But it's also true in the other way around. If we have covering of U1 and covering of U2 and isomorphism between them on the intersection, we can glue them along this isomorphism and get a covering of U1 union U2. So this fiber product is just equal to this category of covering of X. So this functor is just an equivalence. Okay, and now everything will follow from the following exercise. Let gamma 1 to gamma 2 functor between groupoids. Assume that the pullback from what we do funct gamma 1 to sets to gamma 2 to funct gamma 2 to sets is equivalence. Then phi, and this is phi epsilon. Phi is equivalence. Okay, again, this is not hard. It basically follows from your nether, but maybe even simpler. And so we get what we want, yes, because we had this functor. We wanted to prove this is equivalence. We apply this construction of taking functors to sets, get this functor, which we know is equivalence, because geometrically we know how to glue coverings. So we're using this second exercise, we're done. So of course, if you yes.
Sorry, how did you know that this is isomorphism? Because F can be large as much as you
So,
want.
no, here F is just the fiber product of the two categories.
Oh, you know the fiber product about covering. Okay.
Of the categories of coverings, yes? Because here is something geometric that I know, that in order to describe a covering of X, it's enough to describe a covering of U1, a covering of U2, and the identification between them on the restriction. I know how to glue topological spaces. So I know how to glue coverings.
Great.
Okay, so of course, if you compile everything, it's become much longer than the proof in Hatcher. But on the other hand, all the length is inside its algebraic, except of the homotopy lifting theorem, which is topological. All the rest become pure like algebra, combinatorics, or no topology, no geometry is involved. No notion of continuity involved. And also you can claim that most of it's kind of basic infrastructural things that can be useful in other stuff too. So this would make the theory useful, not that it's make one specific proof shorter, but that you build some infrastructure that you can use in many cases. So I think at some point I heard kind of more high-tech proof of Incumbent theorem that make it even more kind of obvious, but rely on much more infrastructure. And so basically, what is the content of Incumbent theorem? That pi1 commutes with pushouts. And yes, so there are many criterions for when a functor commutes with pushouts, and you basically should apply some of them. But the problem is that everything here is not really working in the actual world of topological spaces, but you want to work up to homotopy, so you have to involve here a higher category theory in order to work. Yeah, another way of thinking about pi1. So what is capital pi1? You start with topological space and you get a groupoid. Groupoid have information about the first homotopy and the zero homotopy. So basically you erase all the information about the higher homotopy. So you can consider it topologically. You can take topological space and kill all the higher homotopy groups. And then you get a topological space with only pi0 and pi1. And the category of topological space with only pi0 and pi1, okay, it is a category, so you should make out of it a two category or higher category. It is equivalent to the category of groupoids. And under this equivalence, capital pi1 is just killing all the higher homotopy groups. And then the claim is that killing all the higher homotopy groups commute with pushouts, which at least very natural. Anyhow, I think I like this proof. I can't say it like I like it more than the proof that appear in Hatcher, but because the other proof is more elementary, but I think both of them are good. Okay, I think it's a good point for a break. So if you don't have questions, maybe we'll start the break now. No questions? Okay, so 10 minutes break. Okay. So everybody's back. Tal, are you back? No, Tal. And who else? Oh, are you here? Okay, so I think only Yotam and Evanet are here. So we can wait another minute. Any questions in the meanwhile?
Are there analogs of Van Kampen theorem to other context size?
What other contexts you want?
Just because you said before that the goal is not only to shorten the proof.
Ah, no, I mean that in general one can use groupoids in they have other applications. But yeah, I didn't find too much. I look for very careful and find too. So Van Kampen theorem. So first of all, you can ask what happens with pi 2, and the answer is kind of disappointing. Yes, it is correct, but what is correct? Even Van Kampen theorem itself, it is problematic if there is non-trivial pi 0 of the intersection, because then it's kind of mixed with pi 1. And the same with pi 2. If I think that if pi 0 and pi 1 are trivial, then it works well. But otherwise, they're going to mix with pi 2. And yeah, you can talk. So what are groupoids? Groupoids as a category, as a two category, it's equivalent to the category or the two category of topological spaces, whose all higher homotopy groups, higher than 2, are trivial. When you define the correct two category structures there. Now you can talk about, I don't know how even to call it, some kind of three categories, or of two categories. So topological spaces with up to homotopy with only pi 1, pi 2, by 0, pi 1, pi 2 non-trivial, and all the others have to be trivial. And this is not a two category, it is three category, and you can define it to be the category of groupoids, and then you can talk about this functor capital pi 2, just forget, or like not forget the functor, but erasing functor to this category when you kill off all the higher homotopy groups, and then commute with coproducts. But to compute coproduct in that category, it's not going to be simpler than, it's going to be hard, yes. Okay, so I don't sure how to write it, but Maki theory. Do you familiar with Maki theory from representation theory? Anybody want recollection?
Is the theory? I mean, I know this theory just as a theorem of what do you get when you induced and then restrict from one to
No
group
other group.
to
Yes,
other.
yes, yes. That is exactly what we're going to do. Okay. So here we're not going to give a shorter proof. Basically, it's repetition of the same proof. Like the theorem itself is rather trivial, so it is in algebra. We reformulate it to another algebra, so we didn't do anything. But we are going to give it a better context, I think. So we have a representation of some group H, which H1, sorry, which happens to be a subgroup of a group G, and which have another subgroup H2. Rep of G, and we have a functor induction, which I think it's, if you do infinite groups, it's important to take here small induction. Rep H2. And here we want to talk about the restriction. And you want to understand what's going on when we apply this functor and then apply this functor. And you know the answer. The answer is maybe not very satisfactory. Okay, it's very useful, but maybe its formulation looks a bit weird. You have double cosets, and then you pick up a representative of each double coset, and then you get some intersection of two groups, and you take, so instead of taking first induction and then restriction, then you can take first restriction to a smaller group, to intersection, and then induction, and take direct sum of all of it. And the proof is very simple, but here maybe the hardest thing is the formulation. So the language of groupoids allow us to see where this formulation comes from. So what is representation of H1 is the same like representation of the corresponding groupoid to H1. So this was, so let's do Mackey theory for groupoids. Mackey theorem for groupoids. So let gamma 1, gamma 2, gamma 3 be here phi and here psi be groupoids. So what we want to commute. Now you remember that if gamma 1 is BH and gamma 2 is BG and H embedded in G, so if we want to understand the induction, we should take phi lower Schrick, like the functor of phi lower Schrick. So we want to compute what happens when we do the functor of phi lower Schrick first, and then the functor psi upper star. So phi lower Schrick, I recall it is a little induction. If we want larger induction, we have to do phi lower star, and then Mackey theory. As far as I remember, just am I right? Maybe I don't know. Maybe it will work. Yeah, probably in this case, somehow surprisingly, we can do both. But I prefer to keep it this way. Yeah, I remember that I already thought about it last time I taught the course, and I think the answer was that we can do both. Yes, it's okay. We can do both. Yeah, so we can do here either Schrick or star. I will explain at the end why. So we want to compute this composition. And here is the answer. We have two groupoids, so we can consider this Fourier product gamma 3 with gamma 1 over gamma 2. And here we have phi prime, and here we have psi prime. And now the claim is that this composition is canonically isomorphic. Yes, it's functor, so it's canonically isomorphic to first apply psi prime upper upper, yes, upper star, then phi prime lower Schrick. Okay, so I claim that this is just a direct generalization of Mackey theorem. And here you see where the double cosets coming from. So if we have H1 and H2 inside G, so we can take BH1 times BH2 over BG. And here you leave the word of groups. Yeah, so even we started with groups, H1 and H2 are groups, and G is a group. So you think about these groups as groupoids, but then when you take the fiber product, you get a groupoid which is not a group anymore, which is not connected. It has non-trivial pi 0. So of course you can describe it in terms of groups, but then the description is going to be ugly. And the description in terms of groupoids will be very natural. So let's see what is the fiber product in terms of groupoids. We have to take object here, and isomorphism between them after you consider them as objects here. But those are all BGs. There are no too much objects to choose of. There is one object here, one object here. So, and they both go to, of course, to the same object here, but there are many isomorphisms between this object to itself. And so the objects of this thing in the most standard definition. So of course, the fiber products have many different definitions and they can give different categories which are not isomorphic but only equivalent. So the set of objects is not well defined, but yet if you start with a naive definition, you get to the set of objects, it's the entire group G. And what are the morphisms? So it's easy to see what are the morphisms between two elements X and Y. So more, let's call this category some name F. In F between two elements G and A, or G and G prime, say, is a collection of all H1, H2, such that H1, G, H2, maybe I need to write inverse, but it doesn't. No, let me write inverse, equal to G prime. So, yes, this is rather easy to see that morphisms between two objects here is exactly this. So of course you see that this is a groupoid. It's not BG, but it's equivalent. So BH1 times BH2 BG is equivalent. You can take co-product over all its isomorphism classes, and in each isomorphism class you take the automorphism group. But this is a quotient groupoid, so we know what are isomorphism classes. Isomorphism classes are just double cosets. And each time we take G, the automorphism group, which is exactly GH inverse intersect H1 and B of this. So you see here how you get this answer in McKee theory just from fiber product of two groupoids. You start with two connected groupoids, or three connected groupoids, two connected groupoids over one. You take fiber product and you got not connected groupoid. And this is the reason why in McKee theory you get direct sum over many things. Okay, so now this theorem, I will leave it to you as an exercise, but I will say it's a trivial case, a case of sets, and the general case is not much harder. Yeah, so this is another, how do you say it's extreme of McKee theorem. McKee theorem is for groups of type BG and or groupoids of type BG, and then other extreme are just groupoids which are sets. So we have X, Y, Z are all sets, and here you have X times Z over Y. Yeah, so this is something very general that's called base change. That the idea is that yeah, it depends how you read it. Maybe you should read it a bit differently. Yeah, this time I will take 90 like 45-degree reflection, so transposition of the diagram. It doesn't really matter. So I want to first push downstairs and then pull to Z, or oppositely first pull here upstairs and then push downstairs. So why does it call base change? So the situation is completely symmetric, yeah. So you can take this diagram and draw it like this or like this. But when you think about it, it's better not to think about the symmetric situation. So the horizontal line and the vertical lines should have a different meaning, or at least different intuitive meaning. So vertical lines mean families. So we have family of spaces that is of sets in this case of groupoids or whatever that indexed by Y. And now we change the base, change the index set. So when we do fiber product, it's sometimes called pullback diagram. It's of course completely symmetric construction, but it's often convenient to think about it as something not symmetric. So we have family indexed by Y, and then we want to re-index it. Suppose we have some map between Z to Y, from Z to Y, which means, what does it mean? It means that each index each point in Y, it have more than one name or have some names, maybe less, maybe doesn't have names at all, and those are elements in Z. So the family will be basically say family of the same objects as before, because the fiber of this map and this map are the same fibers, but the name now by different names. The names will be before the index was points of Y, and now the index was points of Z. Yes, is it clear why I call fiber product reindexing or base change? And now we have some direct image construction. What is direct image? It's something that happens more or less for over each point separately. It's something like integration over the fiber, direct sum over the fiber, some operation over the fiber. And we can first perform this operation, go downstairs, and then reindex. Or we can first pull back, which basically means that now we took our sheaf or whatever we had, and we put it back here. So it's the same sheaves over each fiber, it's the same sheaf. And so sheaf over X, we can think about it as a family of sheaves over the fibers, and the fibers are indexed by Y. So it's the same family of sheaf, but we re-indexed it. And now we do this operation of push forward. So let's do it for the simplest case of sets. It's really tautology. Yes, so we have functor from a set to vector spaces. What does it mean? It means just assignment for each point in the set, a vector space. So let's give it a name, F. So f of x is just a vector space for any x in x. So now let's do the first construction. We can do, let's call it this vertical, I don't remember what the word, so let's call it phi and this psi. So phi lower star of f at point y is just equal to direct sum of over all x in phi inverse of y f of x. Okay, and now we want to do psi upper star of phi lower star of f. This is not star, this is Schrick because I took direct sum and not direct product. At point z. So it's again the same direct sum, but now x is not in the fiber of y, but in the fiber of psi of z. F of x. So this is the first composition. Let's see the second composition. So this is psi prime. So we want to compute psi prime upper star of f at some point. What is the point? It's some point here. So let's call it x comma z. X comma z. Okay, so this is just f of x. We don't care about z. And what is phi prime lower star of a lower Schrick, sorry, of psi prime upper star of f at point z. So this is equal to direct sum over all fibers of z here. We have z over all the fiber of z here. So we have the fiber here. But you know that the fiber of z in the fiber product is the same like the fiber of its image in under phi. So let's do it in two steps. Direct sum all the pairs x comma z in the fiber product x z y, and then we do just f of x. what is it equal to? What are points in the fiber product over with second coordinate is z? It's the same as all points of x, such that if you apply phi to them, you get psi of z. So phi inverse of psi of z. And this is exactly what we get here. Yeah, so we use maybe the most important property of fiber product, that it does not change the fiber. That if we have a fiber product, the fiber of a point z here is the same like the fiber of psi of z here. So this was all in the baby model of sets. It worked more or less equally as simple, a little bit more cumbersome, but with no problems with group points. And you see that we could have taken a direct sum, and we could have also taken direct product. It will give the same answer. So if it's finite set, it's obviously the same. But if it's infinite set, it's something has to be proven, but it is correct. No, sorry, nothing has to be proven. If it's infinite sense, there are two different objects, but just the same argument works. So it works the same. Of course, we need to be consistent. If we take here phi lower star instead of phi lower shriek, so here we have phi prime, we also have to take phi prime lower star. And not phi prime lower shriek. So why did said about star before that I like shriek more than star? So base change is something really very, very general in mathematics, in geometry. So each time you have pullback diagram, it's often convenient to think about it in a non-symmetric way. So you have the vertical arrows are families, and the horizontal arrows are changing the base, the parameter set. And then you want to say that various construction, like vertical construction, like various kinds of push forwards, some kinds of integrations, you can change the names of each fiber, but still if they happen fiber by fiber, you don't really care. And this have one weakness, that in general, it will not work in arbitrary way. So usually we have, like in some settings, you have two kinds of push forwards, and in general also two kinds of pullbacks. You have push forward with shriek and with star, and they are different. You saw it here in sets, in shifts over sets. Direct sum and direct product are different. And in shift over group points, you can see even more general examples. And induction, little induction, and large induction is different, and invariance and co-invariance are different. So you see that they're kind of different. And you also sometimes have two pullbacks. You don't see it in sets, and I will explain in a moment why not. And you also don't see it in discrete groupoids, in groupoids of the types that we discussed now. Like not topological groupoids, but actual just groupoids. But you will see it in topological spaces, and you will see it in topological groupoids. And if you want base change to work in general, you need to choose. Either you're working in vertical lines, you're taking shriek, and then in horizontal line, you take star, or the other way around. In horizontal line, you take star, you take shriek, and the vertical takes star. You cannot take star in both. So the reason it worked here that for discrete objects like sets or like groupoids, but not topological ones, there is no difference between, there is only one pullback. There are two push forwards, but only one pullback. And And you can see that we even said it, yes, that we say that this is pair of adjoint functors, and also this is pair of just for the other direction. Yeah, I don't remember who is in what direction, but still this is also a pair of adjoint functors. So this functor pi upper star have two adjoint, and usually it will not be the case. What do I mean by usually? If you have some topology involved, it will not be the case. Pi upper star will have adjoint only for one direction. And there will be another version of pi upper star, pi upper shriek, that will have adjoint for the other direction. So you will have 4 functors and not 3. And the reason why the thing work here is that sometimes lower star and lower shriek coincide, and sometimes upper star and upper shriek coincide. And when lower star and lower shriek coincide, you already saw if the direct sum is finite. If direct sum is finite, it's the same like product. If the group is finite, invariance and covariance are the same, assuming a working characteristic 0. So, and the general, like the topological analog of finite is compact. So if everything is compact, then you expect lower shriek and lower star to be the same. And often this is called like proper push forward, and this is called push forward. Or this is called push forward with compact support, and this is just push forward. Like in homologies, you probably know that homology or cohomologies with compact supports and just usual cohomologies. And so in compact situations, they are both the same. And those two guys, in fact, those two guys, they will be the same in the dual situation to compactness. And you probably, if you know about Fourier transform, you probably know that the dual thing to compact is discrete. Yeah, for example, if you have a abelian group, you see it in many cases in mathematics. But if you have topological abelian group, say locally compact abelian group, there is a notion of Pentagon dual. And Pentagon dual maps compact groups to discrete groups and discrete groups to compact group. If you have Fourier transform of, say, compactly supported function, then it is very, very smooth. So it means that locally it behaves very, very good. And okay, it's not exactly like discrete, but this is the direction we talk about. Yeah, so there is some duality between global behavior and local behavior, and compactness is the best global behavior possible, and discreteness is the best local behavior possible. And indeed, if we have a map phi, so in order phi lower star and lower shriek to be the same, we want that the fibers will be compact, or we want the map to be proper. And if we have a map in order to the upper shriek to be the same, we want that the fiber will be discrete, or more correctly, we want the map to be covering. But yeah, the fiber should be discrete, but also it should work in families. If covering, or you don't even need covering, you can have a Tal map, like local isomorphism. But still, so in our case, in our baby model of sets, you just don't see it. So you only see this become the same like this. And it gives you the illusion that you can make push forward with either shriek or stars. And this is not exactly true, because you have to be careful. If your vertical arrows are shriek, then the horizontal should be stars, and the other way around. But since you pull back along the horizontal arrows, your star and shriek is the same. It means that you can also push forward with star or with shriek, although they are not the same, but the base change will work. So this is warning, you will see base change in algebraic geometry, algebraic topology, D modules, whatever. It will not work there as good as it works here. Okay, any questions about McKee theorem and base change? No questions? Okay, so I think it's first time that a lecture went faster than I thought and not slower. So let me see what is the next topic. I did not prepare to it. Yeah. Teaching. Okay, it seems that the next topics are two categories. It's a big one. So, yeah, I think I can start. We have more than 20 minutes, so let me try to say something. So we want to talk about two categories. Oh, I'm sorry, I will disconnect it in a moment. So, probably today one can just say about infinity category and then substitute infinity equal to 2 and it will be enough. But I don't think it's a good idea. Maybe it's just because I was not born today, but almost 40 years ago. But still, maybe it's worthwhile to see the difficulties and see why it's become harder and harder, and why there is another approach that kind of make all the way to infinity for free, but this free, of course, have its price. So let's define two category. The two category. Okay, so of course we want to start with some collection of objects, and we want morphisms. And the only thing that we say is that this time morphisms between two objects will also form a category. And we saw that it's kind of natural if we talk about the collection of all categories. So morphisms between two categories are functors, so they form category. So if we have two objects, x and y, we have more between x and y, and this is a category. But now we want to talk about composition. Okay, it looks easy. We have x to y, y, z, and then we have the composition for more xy times more yz to more xz. Okay, so this is not mapped between two sets, it's a functor, no problem. I didn't describe Cartesian product of two different categories, but it's very easy to define what it is. But you don't even need to do it. Yes, you can just say we want functors that have two variables, so it's functorial on the first one and functorial on the second one. This is enough. Okay, we're happy. But then we recall that there is one axiom, one non-trivial axiom in category theory, which is associativity. There's also unity, but it's less interesting. Okay, so what we want to say, we have x, y, z, and w. And we have, let's go right like this, more xy, more yz, more zw. So we can first compose the first two, more xz, xz, more zw, or first compose the second two, And then here we can compose whatever left, more xw, and also here. So we get a diagram. And we want this diagram to be commutative. But this is diagram of categories. So what does it mean to want to be commutative? We want that the first composition will not be necessarily equal to the second one, but should be isomorphic to the second one. So we want to have what's called associator. If, let's call it x, y, z, w, between the first composition, let's call it by some name, and the second composition, first and second. And it should be isomorphism. But once we say that, so this is very typical in higher category theory. Once you say that two things should be, before they was isomorphic, so now equal, now they have to be isomorphic. But then you have to be more careful. You have to say you are given an isomorphism. This is also additional structure that you need. And once you get an additional structure, you need to ask whether it has to satisfy something. And the answer here is that yes, it has to satisfy something. Because what now we have 4 objects already. What happens when we have 5 objects? X, Y, Z, W, and I'm running out of letters in the English alphabet, U. And then we'll see that we'll have 2 isomorphisms, and we want them to be the same. And what is usually done in this case, we draw the Pentagon diagram. So, okay, but I will stop to use this cumbersome notation of diagram of categories, but I will just say, assume we have element here and element here and element here, and I will describe it element wise. So because okay, what we do on morphisms is okay. I will explain the end why it's enough. So we have u x, y, z, w, v, say f, g, h, I. And now we can compose them. And the idea is that no matter how we compose them, we get the same thing, no matter how we put the parentheses. And moreover, we get the same thing, meaning we get isomorphic things, and all the possible different isomorphisms are the same. So let's see what isomorphisms we have. So we can start from the beginning. F, G, and then H, and then I. Yes? And now we can try to move the parentheses. Let's see how it's typically done. Yeah, I should have checked it, of course, before. But I think we can. Okay, maybe we start with here. So when we use the left parenthesis to the right parenthesis, we have a morphism. Otherwise, we have a morphism to the other direction. F, G, H, I. Now F, G, H, I. We still move from left, the first two to the second two. And now 1, 2, 3, 4. F, G, H, I. Okay, but now we have another way to get there. We can move here.
FG composed HI.
FG compose HI. Like this. And we have a map in this direction because we move from left to right. And here, what direction do we have?
Again, left to right.
So it's just one. Oh, yes, it is. FG Yes, we break this one and then let's wait. Okay, so we have 5 guys here. So this is called the Pentagon Diagram. And so we can think about the 5 guys, but you can think about there's 2 ways to come from here to here. And this time, the things that we have in the vertices of this pentagon are objects in a category. And the arrows are just elements in sets, they are just morphism between objects in the category. So we can actually ask them to be equal. So we want this diagram to be commutative, just commutative on the nodes, because there's no meaning to ask things to be isomorphic. So yes, so this is the Pentagon diagram, and the definition of the category, it's like this. So also there is this thing with identity morphism, but it is not a big deal, so I will ignore it. So it's a collection of objects, a class of objects, a sets of objects, never mind. For any 2 objects, set a category of morphisms. For any 3 objects, functor of composition. For any 4 objects, associator as a morphism between 2 functors of compositions, of like compositions of composition, like of this diagram. And for any 5 objects, we want the Pentagon diagram, corresponding Pentagon diagram, to be commutative. Now, so I can say it in 2 different ways. The way that I say it now, I took any 5 objects and 4 morphism between them, and then I want the Pentagon diagram to be commutative. So in 4 functors between them. Oh, okay, maybe I should call it morphisms. So 1 morphism, so elements in a category, but they're not necessarily functors on the nodes. It's some category. And of course, you can ask, why I didn't say anything about morphism between those functors? Because indeed, what I should have said is that I have 5 objects, and I don't fix some 4 functors. So I have the collection, this quadruple multiplication of morphism between x to y, y to z, z to w, and w to v. And each of these vertices in the Pentagon diagram should be actually a functor. A composition functor that have 4 variables and 1 output. And the composition functor depends on how you put the parentheses a priori. And then this diagram should be a commutative diagram of functors. The reason that I don't say it, because I already know that each of these arrow coming from morphism of functors. Now it's morphisms of objects. Yes, morphisms of those guys, which are objects in category, but in fact it's coming from morphism of functors. So all the additional information is already there. And if I have diagram of functors and I want to prove that this diagram of functor is actually a commutative diagram, sorry, diagram of morphisms between functors. So the object in this diagram is functors, and they want to prove that the diagram is commutative, but I already know that the morphisms are morphisms of functors. So in order to check the commutativity, it's enough to apply all those functors to each specific object and say that the diagram that I get is commutative diagram of object. So it makes my life a little bit easier because I can write it like this. For any f, g, h, and I, some diagram is commutative. Instead of saying the following diagram is commutative, and here I should write composition number 1, composition number 2, until composition number 5, and then to define each of the compositions 1 to 5 as with some long diagram of arrows like this. Yes. So it makes my life a little bit simpler, not really important. So let's do examples of 2 categories. In fact, let's do 1 example, and then and then we'll talk about related things and then more examples. So the most basic example of 2 category is a 2 category of all categories. And if you look at this most basic example, you can think that I just wasted 15 minutes of your life, because associativity in functors between categories is actual associativity. If you first apply one functor and then apply another functor, and then apply third functor, it completely doesn't matter how you did it, and you actually will have associativity on the nose. You will not have isomorphism, you will just have equality. Before we said that we never have equality in categories, but okay, we never supposed to have equality, we never look for equality, but sometimes we do get equality. And this is the case. And you can think that if it's so archetypical example as all the categories, so maybe it's always the case. And in a sense, you're right. It always can be made to be the case. Any two category is equivalent as a two category. I should explain what does it mean. To another two category in which the associativity will be on the nose, so it's called strict two category. But sometimes it's really not convenient. And so now I want to give many examples where it's really not natural to assume associativity on the nose. And for this, I want to talk about the notion of monoidal category. So here I telling the story backwards. So you all know what is a monoid. Monoid is like a group but without inverse. And now you can imagine that somebody in second course of like in first course on group theory will start with a definition of a category, and they say, okay, important special case of a category with one object, it is called a monoid. And then important special case of monoid, a groupoid with one object, this is called a group. So of course you will say that this is a bad idea to teach what is a group, but this is exactly what I'm going to do now. So definition, monoidal category is a two category with one object. So maybe I should be more accurate. It's exactly like in the case of monoids. So two categories, one object have a bit unnecessary, one piece of unnecessary information, the name of this object. So I don't really care about this object. I only care about its endomorphisms. Its endomorphism going to be a category, but this category will have an additional structure. It will have a composition structure. And this additional structure is called monoidal structure. And it has to satisfy something. What it has to satisfy? It has to satisfy that there is an associator. It is associative in the sense that there exists an associator. And this associator doesn't have to be identity, so it's not an equality, but it's some morphism, and then this associator have to satisfy the Pentagon diagram. And also it has to have unity because it's monoidal category. So monoidal means that it has unity. So and unity is just identity functor in this language. So we have this nice definition of monoidal category. And so in monoidal category, usually we don't call the objects morphisms. We just call them morphisms because we just call them objects because there is no meaning to talk about the one object. And we don't call the composition. We just call it tensor product. So notation-wise, monoidal category is usually denoted like this. We have a category and an operation, tensor product. So you all know tensor product in different settings, but in general, I said before that there is no like one canonical way to define what is tensor product. But to give a tensor product is just give some additional structure on the category, and this structure called the monoidal structure. And now, example of monoidal category. So maybe here the most basic example is vector spaces together with standard tensor product. And this, unless you define some really weird definition of a tensor product, would almost never be associative on the nose. So if you define, you have to choose some definition of tensor product. Yes, you can't just say, oh, at least not easily. You can't just easily say that tensor product is defined by its properties, because now you want some actual functor to work with it. But let's define tensor product not by its properties, but by its by some explicit construction, like span of all pairs v1 tensor v2 modulo something. And then you see that, of course, it's not associative on nose. When you take v times w times u, you get two different spaces depending on how you put the parentheses. The elements going to be different, but of course they're going to be isomorphic, and this isomorphism is very natural, and of course it will satisfy the Pentagon diagram. I can say it's an exercise, but it is kind of a boring one. It's really not hard mathematically, but if you want to write it down, it also will not be fun. So you can just start to think about it and convince yourself that it's not interesting enough to continue to think about it.
Can you explain how the example is a monoidal category? The vector spaces are the morphisms here.
So this is what I explained before, that when we say monoidal category, I said definition monoidal category is a two category with one object, but the terminology is different. Yes, I use it in different way. So monoidal category is a category together with an operation, which we call tensor product, such as if we will just consider some abstract object with some name, I don't know, P, and then the category of endomorphism will be our category C, and instead of composition, we will take tensor product, then we will have the Pentagon diagram, so all the axioms before. Exactly as in monoids, yes, you can say monoid is a group, is a category with one object, but on the level of words, you say differently. You don't call the elements of the monoids morphism between your object and itself. You just call it elements, and you don't call product in the monoid composition. You just call it product. But information-wise, it's the same. So yes, you can consider vector spaces as monoid, like as a two categories. So you have one object, let's call it point, and morphism between this point object itself are vector spaces, and composition of two vector spaces is a tensor product, but you don't do it usually. You just say you have monoidal category, you have vector spaces, and you have tensor product, and it satisfies the Pentagon diagram. So you have associator, and it satisfies the Pentagon diagram. Okay, so now we are out of time, so I think it's a good point to stop. Yeah, so maybe better point to stop was 15 minutes ago, because then we actually finished the first part of the course, and maybe the basic part, one category stuff without actually going to higher category theory. So, any questions? No questions. Very good. So I will see you in a week.
Thank you very much.
Thank you.
ביי.
גיא, אתה יכול להישאר דקה?
כן.
מצוין. רק בוא נחפש הקלטה.